So student, this is the real embedded as far as industry is considered because whatever that 8051, 89C51 or the processors and other controllers, but ARM controllers are very important. Okay, so for the embedded system design, industry point of view, product development, uh, this particular topic is very important and it will leads to the various type of the controllers with the industry grades afterwards. But that's why the initial embedded C best this is necessary to understand.
Yeah, nice.
And definitely afterwards, Linux is also important by that way to understand.
That is real time on operating
RTOS,
system altogether.
yeah, yeah. Embedded system is an advanced embedded or something. The
Yes,
RTOS to understand is necessary.
right.
Yeah.
Okay. Yeah, thank you, sir.
Yes. Yeah.
See here, so in the last session, we have seen some the basic architecture of COM and Cortex M3. And what is Cortex? Why they are called as Cortex? Anyone? And what is this version known as? Anyone? So last session we have discussed what is version one, what is ARM. You're not remembering. Just I will just recall this. Okay. So the version, whatever V1, V2, V3, V4, they are referred to as instruction set architecture. ISA architecture 1, architecture 2, like that. Okay. This family, whatever it is mentioned, this is the hard core. Okay. Core of the ARM. Okay. And this is the architecture what they follow. Now, from our version 7 ISA architecture onwards, we call ARM as Cortex. Okay, so why we call them as Cortex is it comes on a not on a single chip, it comes on a single PCB. Okay, so just like an Arduino board, we have ARM board. Okay, so this version 7 boards onwards, version 7 ARM versions onwards, we call them as Cortex boards. Okay, and these Cortex boards have different variations like A, R, M. Okay, A refers to the application specific, R refers to the real time, and M refers to the microcontroller profile. So for most of the academic purpose, we will be using Cortex M profile. Okay, and for doing some projects also, we'll be doing Cortex M boards. Okay, when it go to the industry, you will be using Cortex A boards and Cortex R boards. The only difference is that is real time. Okay, Cortex R means Cortex A means the application profile, application process. Now, this uh, secure core and classic, these are for the developers of the core itself. Okay, so those who develop the core of ARM, they will do the secure, they will follow the secure core or classic model. Right. So as said, the instruction set architecture is a three-stage architecture. Okay, where this thumb technology, okay, will come into picture. Thumb technology in the sense usage. Suppose say you have an higher end processor, but you have the data of lower end. Means we have a 32-bit processor, but we have a data of 8-bit only. At that time, when you process that 8-bit data with 32-bit processor or a controller, so it has to perform on the complete 32 bits. So your 8 bit has to be converted to 32 bit data. Okay, and then it has to process. For that, it is going to take some time. Okay, so this time is reduced with the introduction of thumb technology. So what is this thumb technology is? It supports the lower end of data instructions. Okay, like 16 bit or 32 bit or even 16 bit also. What? uh, that you sent. That's all. That is what they said. Yeah, you just sent it. Means your that is clear. That's all. I again give it will give to me only at the end. See, he's not taking any responsibility. He's just coming. He's just telling that. That's all.
So far, my concern is other faculties get the mail that forward the camera ready paper, forward it. That also I didn't get it.
Forward the camera ready paper. If any corrections are there,
Okay. If there is no correction, nothing.
no correction. CFT, your copyright is done. Closed.
CMT and copyrights is done for all the four papers. Two papers got correction, two papers I corrected and sent the mail.
Send the back. Over.
Ganesh mail ID was in CC. For him also I sent it.
Fine.
To
Reply all. Reply
Huh?
all.
This is done. Now you gave me some three mail IDs to drop the conference papers. Correct, na? For that, what I will do? This antenna paper I will drop, or I will do that work and I will drop. That robot.
Which robot?
Movable robot, water cleaning robot. No work.
After this, I'll come and go. First, complete that discover. Discover you complete. Finished. Then set the paper. Yeah, sorry for the interruption. Yeah, so this was a three-stage instruction set architecture. Okay, so this thumb 2 and thumb technology. Okay, will process the lesser instructions. Whenever we use these instructions, okay, it will adapt to the data size and it will be processed so that the processor time will not get wasted. Okay, and the three-level instruction three-stage pipeline design includes fetch, decode, and execute. Okay, so these things we have seen. Now the actual architecture. So the architecture of ARM Cortex. This is known to be a Cortex board. Okay, in the Cortex board we will be having the processor core somewhere. Okay, so which has an instruction fetch unit, decoder, register bank, ALU, then memory interface. Okay, then we have interrupt controller, which we call it as a network nested vector interrupt controller. Okay, then we have the traces. Okay, so which we have a memory production unit in addition to that on the Cortex board itself. Okay, so which will be connected to the buses. Okay, the code memory bus, all the buses, right? Now, what is this NVIC, the nested vector interrupt control? Okay, so it is a built-in interrupt controller. Okay, the number of interrupts are customized by the chip manufacturer. So it depends upon which manufacturer has taken this Cortex M3, and they will customize the interrupts. Okay, then it supports the nesting of the interrupts. Nesting of the interrupts in the sense when we process an interrupt, again if one more interrupt occurs, okay, then how this interrupt is going to be processed? There are two ways. One is either it has to stop the present interrupt processing and it has to give the preference to interrupt, the latest interrupt it has to process, and again it has to come back to the previous interrupt processing. Once this interrupt is completed, it will come back to the original. Okay, so this is usually a normal procedure, but uh, here we can have some dynamic prioritization. Okay, so based on the priority assigned, okay, the interrupts will be processed. Okay, so why we call them as dynamic is this priority level can be changed as and then needed by the programmer. Okay, and we have a facility to mask the interrupts also. Okay, so we can mask or unmask them. Then we have the other main feature of ARM Cortex 3 is we'll have an instruction fetch unit, decoder unit, ALU, and a register bank. Okay, so fetch unit is used to fetch the instruction as usual. Then we have a decoder section which will convert your fetched instruction, okay, to mission to ALU understandable, that is your opcode. Then we have an arithmetic and logic unit to do the mathematical and logical operations, and we have the register bank. This is the core actually. Along with registers, okay, along with ALU we have register banks which will have 32-bit registers. Okay, so 32-bit registers, right? So out then this that register bank has 13 general purpose registers, each of size 32-bit, and we have two stack pointers. Along with that, we have link register, program counters, okay, and then program status register. Okay, so altogether if you see 13 plus 2, 15, 16, 17, 18. Okay, 18 plus some special registers. Okay, so this is the core of ARM Cortex 3. Okay, then we have an MPU. So this is an optional thing which was in M3 boards, but in M4 they are made it mandatory. That is memory protection unit. Okay, so this MPU is used to protect the memory contents by making the memory regions read-only or by providing some privileges. Okay, then we have interconnect. Okay, so how the data is processed between the between the processor and the external bus, the processor and the memory. Okay, and the processor and the registers. Okay, so this is interconnect. All right, and the main bus interfaces are, we have code memory bus. Okay, so again in code we have I code and decode. Okay, so I code bus is 32-bit bus. Okay, which extends from four zeros to four zeros to one triple F and double F double F. Okay, so the thumb instructions fetched, okay, or in word size. Okay, and when it comes to the decode bus, okay, so decode bus is a 32-bit bus which can access the memory regions as in your I. Then what's the difference between I code and decode? So I code is specially located for your thumb instructions. Okay, whereas decode is for the normal instructions, right? And alternatively the but the Cortex M3 will use whichever the bus which is available then. Then we have a system bus. Okay, so system bus used to access the memory and peripherals. Okay, so through the SRAM, right? And it is again it is an 32-bit bus band. Okay, then we have a private peripheral bus, so which is based on APF, okay, APB and AHB. So any doubts? Students, regarding the buses, any doubts are there? Fine then. So if you are okay with this, then we'll go with the next part. That is debug and tracing. Okay, so the processor contains the several system debug components, okay, that facilitate tracing and profiling. Then it will check for the breakpoints, then watch points, then code patching, like this. Okay, so now to understand the programming of ARM, okay, either it can be in ALP or our embedded C. Okay, so we should know what is the memory system and how they are mapped. Okay, so if you see the memory mapping, it is about 4 GB, isn't it? So that is 32-bit, 2 power 32. It leads to 4 GB of memory completely. So the memory mapping will be in such a way that, so 0.5 GB is reserved for the code. Okay, and hello, hello, yeah, good morning, sir. Sir, yes, sir. Okay, hey, yes, sir. Please tell me this. Okay, okay. Yeah, yes, sir. I'll just check it and I'll get back to you, sir. Okay. Okay. Yeah, can you just, I just forgot the dates. Can you just get the dates, sir? Then July 14th to 19th. Okay, I'll just see, sir. 14 to 19, right? Yeah. Can I call? Yeah, I have applied. I remember. I'll just get back to you, sir, within some 10 minutes. Yes, sir. Yes, sir. Yeah. Sorry for the interruption. Yeah. So this total memory, 2 power 32, so which is shared as 4 GB of memory. Okay. So this 4 GB is distributed like zero point 0.5 GB is reserved for your writing the code. Okay. Then zero point 0.5 for SRAM, right? Then zero point 0.5 is reserved for peripherals for memory mapping. Okay. So mainly used for the peripherals usually. Then we have an external RAM of 1 GB. Then external device. Okay. External peripherals for 1 GB. So totally it comes around 1 plus 2, 2 1 plus 1, 2, 3, 3.5. So remaining 0.5 GB, okay, is exclusively used for the private peripherals, okay, including the interrupt, and this is an nested vector interrupt controller, okay. So this is out of this zero point 0.5 also, no, 0.5 GB, some are reserved for private peripheral buses, okay. So private peripheral buses, again, PPB and SCS, right. So now, as a memory mapping is done, okay, so we'll just review the things. So here somewhere I have mentioned as AHB and APH, isn't it? So what is this AHB bus and APB bus? The students, you can tell. Yeah, somebody has mentioned. Okay, so why each memory block size is a multiple of 0.5? See, this 4 GB is completely our program memory as well as data memory. It is not exclusively for data or exclusively for program. Okay. So out of this 4 GB, you require 5.5 GB for accessing the code. Means the code is always once written and it is not changed. Right. So for that, giving 1 GB or giving of 4 GB completely is no mean. Okay. We have to optimize the things. So that's why 0.5 is reserved for code, point for your data, okay, and remaining for accessing your external memory, external devices. It can be your external memory or it can be your external peripheral, okay. And again, one thing we have to keep in mind is a zero point 0.5 he has given. For suppose if your program is greater than 0.5, okay, you can make use of the other memory also. So this memory is dynamic allocation in nature in ARM, but by default these will be some reserved spaces, that's all, which can be modified in the later days. Yeah, so any student can just tell me what is an AHB and APB. Right then. So fine, no problem. So AHB means advanced high bus technology. Okay. So then okay. So advanced high performance bus technology, right? APB means advanced peripheral bus technology, right? So within this only you will be getting your CAN bus, S2, I2C buses, okay, SPA buses, all these things, right? So we should know the terminology. The AHB, okay, AHB means Advanced High Performance Bus Technology, okay, so which is a component of AMBA. AMBA in the sense Advanced Microcontroller Architecture Buses, okay. So this is exclusively developed in ARM, okay, AMBA technology. Within this ARM, you have AHB and then APB, all these buses. Now the next thing is the thumb technology. So as said, the thumb technology is used for the lower data processing. Okay, so it is not for the higher data processing. Okay, so the two different instruction sets are usually supported by ARM. One is known to be thumb instructions, which are 16-bit. Okay, thumb 2 technology, which supports both 16 as well as 32. Okay, so during the program execution, the processor can be dynamically switched between ARM state and thumb state, okay, to use either one of the instructions. Okay, so the program execution, the processor is dynamically shifted. Okay, so now this is how the complete ARM architecture is. ARM architecture is ARM 7 Cortex M3 architecture is based on this dotted line. Okay, out of which thumb instructions are 16-bit, and thumb 2 technology has been induced, okay, or used for your version 7, okay, which uses both 16 as well as 32, and dynamically they can switch. Okay, so the thumb technology so is an extended the thumb instruction set architecture. Okay, so is an which is powerful instruction. Okay, so I don't want to just read out this theory. Then we'll see the advantages. Okay, so advantages is no switching time overhead is required for thumb 2 to thumb technology or normal instruction. Okay, so dynamically the processor will change by seeing the data sets. Okay, and there is no need of a separate ARM port. Okay, for implementing the thumb 2 technology. The thumb code source files are enough. Okay, and then it is easier to write the program. Okay, then the cortex registers. Okay, so one is the memory. First we understand the memory 4 GB, how it is reserved, and then see why this memory is given is we should see that where the program has to be in this memory range, that is from 0000 to 1F double F double F double F. Only in this range you can write the program. Okay, you can't use memory location from external RAM saying that this memory location you can take it and write the program. Okay, so that's why the memory mapping is important. Now what are the registers which are involved in writing the program? Okay, so we have this many cases, that is general purpose registers we have, then we have stack register, then we have link register, we have program counter, we have special registers. Okay, now see here how this general purpose all the registers are. So totally 16 registers we have. Okay, so out of the 16 registers, the first 13 are used as general purpose registers, right from R0 to R12. Okay, so we have to remind that all the registers are of 32-bit size. Okay, then we have stack pointer. So we have two stack pointer registers. Okay, one is said to be the main stack pointer register, and the other is known to be the process stack pointer register. Then we have R14, which is referred as a link register, and R15 as program counter. Now, apart from these 16 registers, we have some special registers, okay, which are considered as program status registers. Okay, then interrupt mask register, like priority mask register, fault by default mask register. Okay, base priority register, and we have the control register. Now, if you see here the functioning of the registers, okay, the general purpose registers right from R0 to R7, they are considered as low registers. Okay, low registers. Suppose if you want to process with a 64-bit data, then the combinations of low with high has to be used. Okay, so the lower registers R0 and R7. Okay, from R8 to R12 we consider as higher registers. So whenever we are processing with a 64-bit data, so 64-bit data first the lower 32-bit will be stored in R0. Okay, and the higher 32-bit will be loaded in R8 register. Okay, so this is how these two registers are mapped together. Okay, right. Then special registers, as we said, they are the program status register, interrupt mask register, that is priority mask, fault mask, base priority, and we have a control register. Okay, so special register can be accessed only via MSR or MRS instructions. Okay, so MRS is a read the special register, MSR write to the special register. So once we come to the programming, we can understand this. Then program status word, again the program status registers can be subdivided into three status registers. One we call it as application status register, then interrupt status register, okay, and then execution status register. Okay, so all the three registers, again it has to be accessed using the instructions MSR and MRS. Okay, so when we access collectively, it is called as XPRS. Okay, now this is what the registers we have, XPRS. Okay, so first one is APRS, application. So this is your application program status register. So here we store the status of the registers, okay, status of the operations that are performed inside the ALU. Okay, like negative number. Okay, if it is a negative number, this will be set. Then if you get a result as 0, then 0 flag will be set. Then we have a carry flag. Okay, so carry flag will be set or reset. Then we have overflow. Okay, and then we have queue status. Okay, this is known as saturation status. Okay, or saturation operations. Then in interrupt program status register, we have the bits which are reserved from 0 to 8 as reserved for exception number. Then ESPR, so that is your execution. So for execution we have your tracing, okay, then ICI IT, 2 bits of ICI IT. Okay, so collectively this program status word, collectively when it is referred as XPSR, so this all bits are combined and it is reflected as a frame format like this. So 0, okay, then 0 flags. See ICT, so this is known to be the interrupt continuable instruction, okay, or if then instruction status bit. Okay, what is this interrupt continuable instruction? So for suppose we have two interrupts. Okay, so one interrupt has occurred at one time and the other interrupt has occurred during the processing of the first interrupt. Okay, so at that time, okay, so when this bit is set, when this ICI bit is set, so immediately based on the priority, the first interrupt will be executed. Later it will go for second interrupt, or if the second interrupt priority is high compared to first interrupt, the second interrupt will be executed and then the first interrupt will come back, will be executed later. Okay, then T refers to the thumb state. Okay, so thumb state always 1. Okay, so thumb state should be always 1, and trying to clear this bit will cause a fault exception. Okay, why? Because in ARM3 there is the M3 boards and M4 boards, so your thumb 2 technology is inbuilt. Okay, so that's why this thumb state has to be 1. Whereas if you go to M2 boards or M0 boards, okay, so their thumb state uh, uh, is an optional thing. So the programmer has to shift. Okay, so that's why there we have the flexibility to make it active or passive. But in M3 boards and M4 boards, your thumb state will be 1 always. Then exception number, okay, so indicates which exception processor is handling. Suppose 0 by 0 is an exception. Okay, so 1 by 0 is also an exception. So these exceptions we can write a separate exception programs, and the exception number can be given assigned through this execution PSR. Okay. Then interrupt mask register, we have priority mask, fault mask, and base priority masks. Okay, what is this priority mask? So priority mask is a 1-bit register. Okay, a 1-bit register. So when this is set, it allows NMI, that is non-maskable interrupt, and hard fault exceptions. Okay, all other interrupts and exceptions are masked and default as 0. Okay, so whenever we keep it as 1, okay, so it will allow only the non-maskable interrupt and the hard fault exception interrupts. All other interrupts will not be or masked. Then we have a fault mask register. Again, it is a 1-bit register. Okay, when this is set, it allows only NMI, and all interrupts and fault handling interrupts on exceptions are default. Okay, are disabled. So by default, it will be 0. Okay, so because we want to process all the interrupts. Next, we have base priority register. Okay, base priority interrupt mask register, where the registers up to 9 bits will be there. So it defines a mask priority level. Okay, when this is set, it disables all the interrupts of the same or low level interrupts. Okay, so by default it will be 0. So in general, if you want to tell all these registers, priority primary mask register, okay, then priority mask register, then fault mask register, and base priority mask register, they have to be made as 0 by default. Okay, now this is the thumb state. Okay, so this how the thumb state is handled. Okay, so usually thread mode is known to be the normal port. So from thread mode, you can go to the thumb state. Okay. So from thumb state, you can come back to the thread mode at any time. Okay. So this is just an process how the control register will be handled. So the control register is the one which will switch between thumb state and a normal state of. Okay. So the modes of operation. So usually it has two modes, two privilege modes. That is going to be thread mode and the handler mode. Okay, then two modes, then privilege mode and user mode. Privilege mode means complete usage. Okay, so we can no need to switch between this, since yeah, stack we have to refer. So the stack in ARM is based on first in last out. Okay, so first that is in, that is last out, or last in first out. It is just a stack. Okay, so the push data, so whenever the register contents are pushed, the stack pointer is going to be decremented by one factor. So one factor means 4 bytes. Okay, and then the data is being moved. When it is popped, the latest data that is in the stack area will be popped up, and then your SP register is going to be decremented by 4. Okay, so this is how we can use your push and pop. Right. So now we'll start with the instructions. So unlike the 8051, okay, the number of operands in ARM will be 3. Okay, in 8051, if you see, only there are 2 uh, operands. Right. So if you have any doubts in this architecture, you can just raise now. So the forum is open for clarifications. So we can take some 2 to 3 minutes time to handle this questionnaire. Somebody goes, how does the system know where to start pushing and popping? See, pushing and popping, we have to write. By default, it won't push. Only when the interrupt is occurred, okay, the present status of the program will be pushed to the stack area. Okay, that is a default operation. But if you want to perform any push operations or pop operations, the programmer has to write the program. Okay, so push and pop operations, the system will not know. The system is just an hardware. To our instructions only, it will perform. Okay, So like that, if you take interrupt, it is an default instruction. Okay, interrupt is a default situation where the processor will push the data to stack area. Okay, unless that, okay, for all other operations, pushing and popping has to be done by the programmer depending upon the application. Is there any default at the starting address for stack pointer? Yes, we have a default address starting address. Okay, so if you see your memory mapping, okay, so in your memory mapping, so see here, you have a memory map. Okay, so where you have an area which is reserved for your stack. Okay, and where is the stack here? So if you see your memory map, there is no any stack here. Okay, so the stack will be your SRAM. Okay, so the other name of your stack area is executable memory. Okay, and this executable memory is otherwise known as data memory. Okay, and the data memory is your here. So the default stack address will be starting from 3FFF, all Fs, all 7s. Okay, I think the question is addressed. I think only Govind is the one who is just trying to give the how are these arithmetic instructions typically used in separating calculations. See, arithmetic instructions will never handle the interrupts. So for handling the interrupts, that is a separate mechanism altogether. Okay. And coming to the subroutine calculation, we have not yet started. Okay. So we are going to process it now. So there won't be any relation between your instructions and your interrupts. Okay. Interrupts are processed due to interrupts are user defined as well as hardware defined. Okay, through hardware only you will get the interrupts, not through something else. And the user has a privilege to interrupt a process at any time. That is through functions. Right. So any other things?
So, sir, what is the reverse subtract operation?
Hello.
Sir, what is the reverse subtract operation?
Reverse
Subtract?
reverse substrate subtract. See, we have
Yes,
not
sir.
yet started. Okay, so we are about to start this arithmetic. Suppose reverse subtraction is we are doing a minus b, right? So if you want to do b minus a, that is your reverse subtraction.
Okay, sir.
Okay. So we have not yet started. Okay, we have till architecture we have completed. We are about to start the instructions. So one by one we'll do that. So till now, if you don't have that, then only we can proceed with the instructions. No doubts. If you don't have the doubts. Okay.
Yes, sir, you can proceed, sir.
Yeah. Fine. Right. So now see this instructions. Okay. The instruction set. The first and foremost difference between a normal processor, okay, or a controller, okay, with respect to the ARM is your ARM will have three operands in the instruction line. Whereas if you go to your 8051 or 8086, you may have only two operands. Okay, so what are those three operands in ARM is? So first one will be the source. So let us say, for example, we are taking add instruction for performing the addition operation. Okay, if we have add, okay, so add instruction, you have first operand as your destination all the time. Okay, then you have the two sources which are referred. So now here in this instruction, the contents of Rn will be added, so contents of Rm will be added to Rn and the result will be stored in Rd. Okay, suppose if you want to use two instructions, of course that also can is possible, but only the difference is the first instruction is always your destination. So you can see the difference between the first and second instruction. The first instruction we have three operands where Rm and Rn holds the data. Okay, when it is added, when the contents are added, that is loaded into RD. In the second case, the contents are added with are handled with RM and RD registers. These contents are added, and again the result is updated in RD. Okay, so RD means your destination register. Okay, so suppose if you have an immediate data, so the immediate data will get added to your RD register contents, and the result is stored, okay, once again back into your RD, right? So this is what the addition operation will have. So addition operation is straight, okay, and three operands we can use. So as of now, as you are the beginners, okay, I suggest to do the operations with respect to three operands only, so that we can understand the ARM better, right? Once you become at least a proficient, okay, not an expert, at least a proficient, then you may use the two instructions, okay, the two operands in the instruction. Next, we have addition instruction, okay, arithmetic instruction. Then we have ADC, that is your add with carry. Okay, this is same as your the add with carry operation. Then we have one thing called as add W. Okay, so what is this W? So add the register with 12-bit immediate value. So 12-bit immediate value it is. Okay, so this 12-bit immediate value. So Rn will contain 32-bit, and then this immediate will be a 12-bit number that will get added to Rn. Okay, and that will be uh, loaded into RD. So this you can find in these applications you can find in while handling your special functions. Okay, special function registers. Then we have subtraction. Okay, so subtraction, so Rm contents will be subtracted from Rn. Then we called as reverse subtraction. Okay, where the opposite is done. Okay, so if you do the reverse subtraction, okay, so we have Rn minus, suppose Rm, if it is a normal subtraction, Rm will be subtracted from Rn, whereas in reverse subtraction it will be Rm minus Rn. Okay, so usually Rn minus Rm it will be, now it will become Rm minus Rn. So this will be the first number subtracted, Rn will be subtracted from Rm. Okay, then we have something called as multiplication. Okay, so multiplication also we can use two operands or three operands, okay, as convenient. Okay, so yeah, so here Rm is multiplied with Rn, Rd, and the contents are stored in Rd register only. Then in the second case, Rm content is multiplied with Rn and it is stored in Rd. Now we have division, okay, signed division and unsigned division. Okay, so unsigned division, okay, your Rn is divided by Rn, okay, and the quotient and the remainder both are stored in Rd register. Okay, then signed division. Okay, so signed division for exclusively for signed numbers. Okay, whose MSB bit is 1 always. Right. Next, we have uh, multiply and division instructions. Okay, which is a combinational instruction. Okay, so it is here two operations are performed in using a single instruction. Suppose if you want to do multiplication and accumulation, that is addition, with a single instruction, then we can make use of MLA instruction. Okay, multiple accumulate. Then in the same fashion, multiply and subtract. So we have MLS. So then multiply 32-bit number, we have mul. So SDiv, sign divide, then signed multiple and accumulate. So SMLA L. Okay, now what is this L refers here? Actually, the instruction is MLA only. S refers to the sign, the prefix refers to the signed or unsigned operation, and the suffix, whatever you are putting L. Okay, so this refers to long. Okay, long in the sense your 32-bit number result will be converted to a 64-bit result. For suppose if it is an 16-bit result, it will be converted to a 32-bit result. So this L specifies long or short. So short refers to the size of the operand, Okay, long refers to 2 times of the operand. Okay, then similarly we have udiv, unsigned division, then unsigned MLA, right? So that is what two 32-bit numbers uh, are multiplied and then a 64 bit is being added. Okay, so in the same fashion for your unsigned also we have, then unsigned mul long, right? So now see here, so this is what we have seen the examples. Now see, we have opcode, operand 1, operand 2, like this we keeps on going. Okay, so in this our maximum size is opcode, operand 1, operand 2 and operand 3 for our ARM. So let us take a simple example. So yeah, so let us see here, move r0 comma ash 0 cross 1 2. So now here the usage of embedded C will be more useful in ARM. See, this is an ALP, R0 is a register, and ash 0 cross 1 2, okay, is also an hexadecimal number, right? So this you can perform it as ash 12h, or simply you can write as ash 0 cross 1 2, which refers to an ASCII. Suppose if you want to send a character, then it has to be mentioned with a single quotations. Okay, right. So instead of going this, I just read out the instructions, and straight away we'll try to implement in one simulator for understanding, better understanding this. Okay, so we have ADC, add with carry, add AND, logical and BIC, bit clear instruction, then CNM, compare negative, so means the compare one data with 2's complement of another data. Then we have CMP, it's a straight comparison operation. Then we have CPY, copy. Okay, so it is available only from version 6. Okay, then LSL, logical shift left, logical shift right. Then we have MOV. Okay, so MOV in the sense copying instruction from one register to other register, then multiply, MUL. Then we have MBN. Okay, so move not, so we can move the negation of one number to negation of one operand to the other operand. Then in order to get the 2's complement, okay, so 2's complement will get negation NEG, OR operation ORR, rotate ROR, subtract with carry SBC, SUB is subtract, test is logical testing, then reverse byte order, that is REV, then X SX TX, signed extension byte, then signed extend half word, then unsigned extend byte, unsigned extend half word, these instructions. Okay, now what we do is all these instructions we will do with the help of this data transfer instructions. Okay, so in order, if you want to perform all those operations, we should be aware of this data transfer instructions, which we call them, which are categorized into four. That is moving between register and register, moving between memory and register, then moving of data between special register and register, and moving an immediate data value to a register. Now see here, instead of using move, okay, so moving the data registers, okay, we can use load and store instructions. Okay, so the other name of ARM architecture is load store architecture. Okay, so what is meant by loading? Loading in the sense getting the data from the memory. Storing means putting the data into the memory. Okay, so loading, so load RB. Okay, LDR is an instruction. B refers whether what type of data type we have to move, whether it is a 32-bit or a 16-bit or any other data type. Okay, so for suppose if you want to move a byte, okay, then it has to be referred as B. Okay, so load byte, okay, to the register RT from Rn. Okay, plus if you have any offset, that offset can be added over here. Then load half byte, half word, H refers to the half word. Okay, so which will copy the data from Rn, the location pointed by Rn and offset to a register called destination register RD. When we do LDR, okay, so complete 32-bit data is being moved. Okay, when if you do LDRD, D refers to the double word. This is how you specify the thumb straight away without specifying anything. Okay, BHD. Okay, so D refers to the double word. So the data from the offset address formed by Rn and offset is moved to the two registers RD1, destination 1 and destination 2. Why two destinations? Because one register can hold only 32 bit. Here we are trying to transfer 64. So two registers are required to hold that 64 bit of data. Okay. Similarly, whatever LDR is referred, the same thing is applicable for STR also. The only difference is your destination will be your memory location, means store a byte of data from RD to the address found by Rn and offset. Okay, store the half byte of data from RD register. Okay, from the from RD to the address formed by the memory to the memory location formed by Rn and offset. Okay, then store RD to offset. Okay, so word to the memory location. Similar fashion, the data from your RD1 and RD2 to the address formed by Rn and offset. Then we have something called as IA. Okay, LDMIA, STMIA. Now what is this LDMIA? So LDMIA, so what it will do is RD exclamation register list. Okay, so if you want to transfer or if you want to load multiple data using a single instruction, then you will use this multiple load and multiple store instructions. Okay, so load multiple, okay, data from the register list, okay, to the register RD. So it reads the multiple words from the memory location specified by the RD, okay, and increments after each and every transfer. Okay, so 16-bit instruction. If it is a store, stores the multiple words to the memory location, okay, by RD, and then increments after each and every transfer. Okay, so right. So this LDM and STM are thumb instructions. So with the thumb instructions, if you want to transfer 32 bit, then you have to use the extension called as .w. Okay, so if you are not using .w, only the half byte or half word will be transferred. So now let us see all these things. So this is the best example. So the exclamation is the in the move instruction specify whether the RD should be updated after the instruction is completed or not. So that we call it as prefixing or postfixing also. Right. So this, yeah. So what we do here, I'll use the workforce. Yeah, so quickly what we do is I'm going to share one data sheet. Okay, so this data sheet you can just complete it and submit to Mr. Vinay. Vinay is there? Yeah, Mr. Vinay.
Yes, sir.
Yeah, so yeah, what is the status of the previous task, sir? The students have completed?
Yes, sir. 12 students are completed, and I clear, sir, already.
Okay. Yeah, so now based on this ARM architecture, because programming we have given the introduction, now we are going to work straight away. So before going
Okay.
to that, the student has to complete this, just like we can make it as an quiz itself, we can conduct it. Okay, so I'm sharing this with you. Can you just handle this, sir?
Yes, sir.
Okay, how I can handle? Through mail or through something else. So okay. So through mail I will send
Through
it.
WhatsApp group also, sir, and mail also.
I think I'm not in the WhatsApp group.
Sir, you can send me by mail,
Okay. Yeah,
and
I'm
I can
sending
forward
again
to
to you.
the students.
Okay. So today at any time after the class is completed, you can just give that and let the students complete the task also.
Okay,
It
sir.
will be easy for them.
Hmm.
Task two, I'm just sending. Give me a minute. Yeah. So I think you have received the mail, sir.
Yes, sir, I received.
Okay. So this you can conduct to the students after today or tomorrow. So that is your wish, sir. This is the second task what they have to complete. So based on that
Sure, sir.
only they can go further.
Sure, sir.
Yes.
And one addition thing, sir.
Sir.
In department we have the experimental kits of the arm.
Okay.
Okay. So for the hands-on for the students in the coming days, because college will get start from the 1st of July.
Yeah.
So even student can work here in the lab with the kit also
Yes, sir,
practically.
definitely. So for
That
that
is
only
also
I just
support.
prepare certain things.
Yeah.
So this is just like a task. Okay. So we'll just work on this and the same code they can implement on the boards straight away.
Yes. Yes.
Yeah. Right. Yes. I'm stopping the presentation now. I'll go with yeah. So we can have a break of 5 to 10 minutes, sir. 5 minutes, and then we'll start the programming straight away.
Okay. Okay. No problem.
Okay. Okay.
Yes. Yeah.
Uh, Sir, we can continue.
Yes, sir.
Yes. Okay. So now what we are doing is we are going to learn this instructions everything because uh, these instructions and the variety of instructions. Say, you have an instruction. Okay. This instruction has to be represented either in thumb or normal instruction. Okay. And this thumb can be thumb instructions or the normal instructions. Once again, can be represented in terms of bytes, used in terms of bytes, then double byte, okay, double word, okay, then half word, right, and then it can be used as long or short, and then it can be used as uh, your IA, incremental or decremental. Okay, so these varieties of that. So if you see all these combinations, okay, so our time will not be sufficient. So what we do is we straight away go to an emulator tool. Okay, okay, so it's a simulator tool where the direct a particular code will be given. This code we will be execute and we'll try to understand how this instruction is being uh, executed. Okay, so for this I'm sharing my screen right away. Okay. So hope my screen is visible now. Say the tool what I'm going to use is an cupulator. Okay, a cupulator to understand this load and store instructions. Okay, so it is with reference to the textbook which is authored by Daniel Lewis. Okay, so ARM assembly for embedded applications, right? So what we do here is there will be a code, okay, so which is written to understand the load and store instructions, and after executing each and every instruction or every instruction we have to fill the data for uh, these questions. Okay, so after step one, after each and every step, what is happening, so that we have to check. So for this we have to just click on the browser. Okay, so once you click on this, okay, so you will go to a cupulator which looks like this. Okay, so hope you are having a visibility for this. Okay, so this is the same program. So now here you can understand from where the memory has been written, or the programs are written. Okay, so first let us first see the code which is given to us. Okay, so load, store, right? So once you click on this, straight away your code will be loaded. Okay, this is your code. This is your memory. Okay, this is your code disassembler. Okay, and this is your editor. So in your editor option you will be having the code that is specified here. Okay, so the same thing you can use over here, disassemble. Okay, and then so once you compile and load, okay, you can see all the data. See here, compile successfully, and in the memory you can see the data which have been executed. But that is not our goal. We have to execute this stepwise. Okay, so we have to stop this. Okay, then step over we have to do it. Okay, so for that F2, so first R1 register. So in the left hand side you can see what is happening, and here you have options to display whether by settings word or double word, half word or byte. Okay, so now see here, restart. Okay, then first step, so you can just make it as word, then you can continue. Okay, so display word, then R1, R0. So I'll just use this. And I just close it again. I will try to open it. So once you load, it is free from errors actually. So that's why it will directly going to the disassemble mode. Okay, so we don't want disassemble mode. We require a compiler mode only. So first we will step. Okay, so see the first step. First, what we are doing, load register R1 with 00000100. Okay, so this data is loaded into R1. Now in the next step, your R0 is loaded with all zeros, initializing the words at 0 as 000. Okay, next move at R1. Okay, at R1, whatever the data is there, that we are trying to store it into R0 register. Okay, so now let us see control M, go to 0010 location. So this is your 0010 location. Okay, so suppose say we are keeping it as 00001234, right? Then come back to editor, then step. Okay, now see into R1 what is moved, 1234 BCDE. Okay, so 1234 BCDE. So what we have loaded, 200. So 00 location, what is there? This is given in your data. Okay, so if you want, just refresh this. Just refresh this. Restart this. Okay, then this 1234 BCD is moved. Then yeah, see here. So this R0 value is being moved. So let us understand this code first. Okay. So first R0 is loaded with some data. Okay. So I just restart this. Now R0, R1 is loaded with 00000100. Okay. So next R0 is loaded with 00. Now whatever the contents of the address 000, that is moved to R1. Okay, so just we are storing the data, right? So the contents of R0 is stored to the point which is pointed by R1. So R1 is pointing to the address location, this location. Okay, so this here you can see the black dots. Black dots means the updated memory. Okay, so now what it is happening here, your R1 is pointing to a location called R1 is loaded with 00000100. So this is replaced here. So whatever the contents in R0 that is there, that is stored into the memory location pointed by R1. So R1 is uh, pointed to 100. So into this 100 you are loading a new value 000. So that's why here it is in black color. Next, R0. Next time what we are doing, R0 is loaded with 1234 BCDH. Okay, load the R0 register. See here there are two ways of representing. So you can represent is equal to refers direct assignment. Okay, so this data is directly assigned to R0 or R1. Next, okay, store the higher R0 into R1 register. So R1 is pointing to where? 110, right? So now come to 110 and see here. So it has been updated. Only the higher byte BCDE is being updated here. Okay, so BCDE is updated. BCDE is updated to your address location pointed by R1. Address location pointed by R1 was 100. So into this 100, your BCD is going to be stored. Okay, next load SHR. Okay, so load SH. Okay, so href is higher. Okay, now see what happens here. Now see your sign higher. So whatever the R0 register was there previous, okay, R0 register was uh, 1234 BCDE. Now what is the status of B? Okay, so B status is B is represented as 1100, not 110. Uh, so uh, B is 11, right? 1011. Now if you 1011, your 1 is your uh, sign bit. Okay, so which is 1, which refers to negative numbers. That has been extended. So what is this LDA SHR will do is your higher byte, okay, from your memory location. So whatever the memory location we have, okay, you are going to load your R0 content. Okay, so your R0 is 1234, right? So in this 1234, okay, your sign is getting extended. Okay, so your FFFB is there, right? So that is getting extended to your BCD. Now see here BCD is there. So this uh, R0 is loaded with your R1 data. Okay, R1 whichever is pointing, and in that data, if your MSB is 1, that is getting extended to the rest of the bits. So the rest of the bits in your R0 is whatever it is there, that is being extended to 111111, which refers to FFF. This is what as sign extension. Okay, next SHR. Okay, again what we are doing, so higher by demonstrate LS. Yes, so it is an unsigned number. Okay, so unsigned number means directly your BCDE is going to be loaded. No, the sign extension will not be done. Even though the MSB bit of B is 1, okay, that will not get extended. Okay, understood this? So 1 minute. Hello, sir. ఇక్కడ ఉన్నాను సార్ మైక్రోప్రాసెసర్ ల్యాబ్. ఒక్క నిమిషం ఇటు రండి ఇక్కడ. Okay, so now this happens. Now we'll take a new data, okay, where your R0 is loaded with 1, 2, 3, 4, 4, 5, 6H. Now this data we are going to store into the memory location 100. Okay, now see in 100 what happens. Only AF is loaded. Okay, BC is not loaded because it is overwritten. Only this data is getting overwritten. చెప్పండి. సాటర్డే నేను బయట వెళ్తున్నాను. 28 కదా. నేను ఎగ్జామ్ వెళ్తున్నా.
అదే అందుకని మీది రేపు డ్యూటీ ఉంది అయితే
రేపా నాకు 26.
26 నేను కన్ఫ్యూజ్ చేసుకోవాలి
26th
వేరే అవుతుంది అట్లయితే ఈ ఇద్దరు ఉండే మహేంద్ర సాగు ఓకే
26 అనుకుంటా 26 ఈ డ్యూటీకి మారిపోయింది అది.
ఓకే
ఈ డ్యూటీ ఆల్రెడీ నేను ఎక్స్టెండ్
వేరే
చేసేసుకున్నా. సో 26
ఇక్కడ వీళ్ళిద్దరిది ఉండే మీది కనిపిస్తుంది మీది ఒకే మహేంద్ర సాగు ప్రాపర్టీ
అది నేను దాన్ని అడిగి
వాళ్ళకి
నాకు 27, 28 కేంబ్రిడ్జ్ వెళ్తున్నా. సార్ so here in the next stage only AF is being transferred. See here, load, store, byte. Okay, so the byte, the starting byte, that is the higher byte is lower byte is your AF. Okay, so which is transferred to the memory location 1000. So in 1000 and 100 already we had BCDE. Okay, so this DE is being replaced with AF. Okay, next sign extension B. So now if it is A, the sign has to be extended. Now all these bits will become 1. Okay, and that value will be loaded into your R0 register. Now see the R0 register, what happens? It should be F, 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 A, F. See, so the sign has been extended. Since your A, if you take AF, okay, the digital representation is 1010, all ones. Now if you take the MSB of this, it is 1. Okay, so this 1 bit will get extended, the sign bit will get extended to all other bits of the register. That is what, okay, so that is what this SB refers to. Okay, so sign extended byte. Next is load byte. Okay, R0 with R1. Okay, so we are going to load this. Simple. Okay, so we are just without sign extension we are doing it. Okay, so without sign extension, so all things will be 0, means as such your memory it will be moved. Okay, next is a simple with LDR. Okay, now LDR R0 is loaded with 1 2 3 4 5 6 7 8, then R0. Okay, so the address location was 100, so here the address location has been changed to 1 2 3 4 5 6 7 8. Okay, then we are going to sign extend the byte. Okay, sign extends the bit in the sense, so 7 8, this for the 7 8 the first byte. Okay, so for the first byte the sign bit was 0. Okay, so this has to get extended, so it will be all zeros and 7 8. Okay, so this is your simple program. So hope this program is very clear to you. Any doubts in this? Okay. Any doubts here? Okay, fine. Then in that same scenario, we'll go to the next one is addressing modes. Okay. So how the addressing modes are used? Okay. So come to the editor. So addressing modes, what are the addressing modes we have? How we can access the data from one to one, right? See, for your better and for your understanding, this data sheets I will share with you so that you can also work individually and understand how these are working. Okay. So we are just there is a program simply an array, okay, a 32-bit array. So where we are defining some words, okay. So BEF, then beef, code, food, and face. Okay. So these are some catchy words which can be used as a data. So that's why we have used this. So this is beef in one word, then the other word is code, the other word is food, and the other word is face. Right, now let us see how this will be. So first we'll start the execution. So array is being assigned to R1, the starting address of the array 32. Suppose if you are putting here as 0 cross, then it becomes a data. Okay, but this is not a data, isn't it? So there is an array. Okay, array, in an array we have defined 4 words. Okay, and the 4 words starting address of this is loaded to R1. Now let us see R1. So again it is been starting at 100 H. So here we have used the 100. Okay, starting address, that's why 100 has been used. Check your memory, 100 memory. So here you can see whatever the data we have defined. BEF, code, food, and face. Okay. So in the first 4 bytes. Okay. So it's loaded with BF, BE, EF, and then next 4 bytes is loaded with code. Next 4 bytes with food. Next 4 bytes with face. Okay. Right. Uh, yeah. So now the first array is assigned to R1. Now let us see how the data is moved. So the first location R1, okay, wherever it is there, that is moved to R0 register, right? Then next time, if you want to copy the value of code, that is your this one, 4 memory locations. So it is going to consume this as one memory location. This is the second memory location. This is the third memory location. This is the fourth memory location. And how it is stored? Anyone can explain this? Why it is consuming 4 memory locations? This is a 32-bit data. Okay, so this is 8-bit, this is one 8-bit, this is one first 8-bit, next 8-bit, next 8-bit, next 8-bit. Anyone? Well, no one is responding. Okay. Okay. See, always in one memory location, 1 byte of data is stored. Okay. So if you take here, you have 4 bytes. Okay, so 4 bytes in the sense 4 into 8, that is 32-bit. So this is the first 32-bit data. This 32-bit data, okay, consumes 4 locations, that is 100, 101, 102. So it's going to consume like 100, 101, 102 and 103. Now from 104 onwards, the second byte, the second word is going to be declared, right? So that's why, okay, in order to access the next data, R1 is, hello, ஆமா இங்க இருக்கு, you are taking it there. Okay, okay, fine. Okay, it's sambar and egg. Right. So first four bytes have been consumed by this. So next 4 bytes will be next address will be 1003. So for next four. So 1000. Okay, 1000. Sorry, 100, 101, 102, 103 has been consumed. Now 104 has to be accessed. Okay, for that plus 4 we are doing. Okay, that is what the offset is. Okay, so R1 is pointing to 1000, comma 4, 1000 plus 4, so 100 plus 4, 104. In 104 you have code, so that will be loaded to R0 register. Let us see whether it is loading code or not. Now see, code is loaded. Okay, next what we do, uh, R2 we are assigning it 8 as an offset. Okay, so instead of writing the direct data, we are using two registers only. So now the next new address location is formed by adding R1 and the and R2. So R2 we have 8. Okay, so this code will consume 104, 105, 106, and 107. So the next data, that is food, will be starting from 108 outputs. So 108 is food. So now that will be moved to R0 register. See food. Okay, next R2 you are adding 2, 3. Okay, right, and then here we are doing something good, that is R0, and then offset is formed by R1 comma R2 comma LSL 2. So what is the R2? R2 was 8. Okay, so R2 is 8 means 0 0, sorry, R2 is 8 means 0 0 0 0 1 triple 0. Now it is added with LSL2. LSL means logical shift left. Logical shift left in the sense 2 times it is going to be shifted. So 2 times means 0 0 1 1 1 0 0 0 0. Okay, so the new address will be C. Okay, or you can say 4 into 4 times it is shifted. Okay, so 4 times, so sorry, R2 is 3, right? Sorry, R2 is assigned with 3. Okay, so 3 means 0 1 0 0 1 1. Now 2 times you are shifting, it becomes 1 1 0 0. Okay, so R3 is, so in your digital representation 0 0 1 1. So when it is shifted or multiplied by 4, it becomes 12. Or the best method is logical shift left. So 2 times it is shifted. For the first shift it will become 1 1 0, and for the next shift it will become 1 1 0 0. So 1 1 0 0 is known to be your C or 12, where your uh, phase is being loaded. So that value, that new offset address will is added to R1, and that is moved to R0. So 3 it is shifted. Now see phase. Okay, so this is how we can make it. Next is post increment and pre increment. So let us say the post increment. Okay, so post increment means first whatever the data that is pointed to with pointed by R0 will be moved to R0, and then it will be incremented by 4. Okay, so first R0 where it is pointing, R0 R1 is pointing to R832, means the first data, that is BEBE. Okay, so that will be moved, and then R1 is updated with plus 4. Okay, so now see here this. Now R1 is, see, earlier it was 100, now it is 104. Okay, now what is pre-increment? pre-increment in the sense before moving the data itself plus 4 we are adding and then R0 is moved. So R1 was updated to 1004 plus 4 is 8. So in 1008 you have food. Okay, so now food will be moved to R0. See here. So this is how you can understand, we can make use of this code and you can understand how the data is transferred between the registers and address locations. Okay, so any doubts in this? I feel this is very handy for understanding this instead of going to Keel and every time you just compiling it. Okay, so instead of that you can just make use of this. Any doubts in this? If you have any question, it is open for. If you are clear, then we will go for the instructions, arithmetic instructions, all these things, how they are, how the data is taken, how the data is modified, everything. And a few worksheets I will share with you tomorrow so that we can have the task as third task. You can just directly open it and you just work on it and get back the results.
Participants, have you any doubt? Please ask. I think, sir, no doubt.
Okay. Yeah, students are not responding actually. I don't know
Mm.
what, yeah. So, but anyhow, they are just coming up with a task that has been assigned to them. So I feel that they are learning something.
Sure, sir, sure.
Yes. Okay. Then I'll go with the third worksheet. That is understanding the addition and subtraction. Right. Yeah, this is very simple thing. Okay. So I told you MSR instruction and RS instruction. MSR instruction to load the uh, the status into an application status register, okay, or your process status register, okay, or if you want to get the status of the process status register, then we have to use an instruction called MSR. Okay, so MRS will load the process register. Okay, RS will take the data. Okay, so if you see here, you have call stack, traces, so breakpoints, watch points, and then symbols, and then counters. Okay, so we anyhow we'll work with these registers also in the future. Okay, so then we have this code separator, all these things we have mentioned, right? So we'll start with this now. Yeah, so it is compiled already. Okay, so now your application register, the status, okay, NZCBQ, that is your negative status, your zero status, your carry status, and your overflow and your saturation status, everything you are clear, okay, by just sending a data called 0. Okay, so if you want to, yeah, so if you want to check this, so you have to locate your PSWR. Okay, next, your R0 is loaded with one value, that is 400000. Okay, now what we do, we are adding the contents of R0 with R0 itself and loading that status to R. Okay, so now let us see how it is going to happen. Now see, so adding the same number will get result in 80000002. Now add yes. Okay, so add C we can use, sorry, add yes. Add S is known to be the sign extension. Okay, so now let us see what happens with sign extension. So there won't be any change. Why? Because it is directly your 32-bit number, and in there your 32-bit number, if you are putting uh, your your MSB is 1 and beyond that there is no number. Now I'll simply modify this with H. Okay, and then I'll start over. Okay, then I'll start executing. Now see here, R1 is moved to 0. So now let us load this value once again. Start. Okay. So start from starting. So for next adding, next time extinction, then sub S. So once you subtract, it will become 0. Okay, then add carry if you have any carry. Okay, so your carry was set, okay, so during the subtraction, so that has been added. Okay, then reverse subtraction, you'll get C. Okay, so reverse subtraction is so R0 value was 4001. Okay, minus 1. Actually subtraction means, reverse subtraction means 1 minus R0. Okay, so 1 minus R0, R0 is 4000000001. So this 2's complement of this will get subtracted from 1, and what are the result we are getting is just simply C. Okay, so this is how we can just work on this uh, addition and subtraction instructions. Okay, so you see that so you go to your compiler and see the settings. Okay, so with the help of settings you can just change the values. So if you want to see the decimal formats, you can see the decimal formats per word. You can see this and see how it is changed. Okay, see 2 words. You see the memory. Okay, so memory is shown in this fashion. So if you are loading it with 4, okay, by default it is 4, right? Trace watch points. Then can make use of the counters. Okay, symbols. Okay. So we'll take one more worksheet for understanding this multiplication, and we'll stop here after this. Okay, so so we are using hexadecimal converters also for verifying our results. Okay, so since in calculator sometimes it may have it and it may not have, so just allowing this. Okay, so let us understand first, okay, what are the values that is given, and then we will just code this. Okay, first R2 is equal to plus 3. So now what happens here? See, 3. Okay, so 3 is loaded. Then R3 is minus 5. So minus 5 in the sense, what is the maximum value? Minus 5. It will be loaded. So that is B. 2's complement of minus 5 is 3. Now what we are doing, multiply R2 and R3. So 3 is multiplied with this. So now we'll just take this copy. Let us see. Okay. So now 3 we have it. Okay. So next is minus 5. So let us see minus 5 by how we are getting minus 5. We are converting decimal to hexadecimal. See here, BFF, if it is a 16 bit, if it is a 32 bit, okay, so all the 32s, all the remaining bits are going to get changed. Okay, so this is one way. Okay, so digital group choose complement. Okay, now minus 3 multiplied with FFP. Okay, so now demo, right? So then we are multiplying these two numbers. We are just stepping it. So when we multiply, so we are getting it as 3 and 3. Now sign extension mul long. Okay, so now your data will be stored in R1 and R0, the multiplication of R2 and R3. So now see R1 and R0, what is happening? The sign has been extended. Okay, next what we do, next load 3, then load 8, and then we are doing multiplication. Okay, so 3 into 8, so that has to be loaded into R0. So this is R1 and R0. Okay, so your unsigned mul long. So this is how you can do this, implement this. Okay, so if you have any doubts, the forum is open for doubt clarifications. Required for revision purpose. Okay, okay, no problem. I'll just share with Vinay sir. Okay, and you can just take it from him, the PPTs.
Sure, sir. आप share कर देते हैं मैं.
Yeah, sure. Okay, so then tomorrow we will do some more worksheets. Okay, and then two worksheets will be given as a task tomorrow. You can complete that.
Sure, sir.
Yeah.
Definitely.